level. Or rather, the application will have a key that all the nodes in that application have a hard-coded key. So other applications don't know how to connect to this application. So this application, nodes from that application can't connect to that one. Of course, it's a hard-coded key, so it's just semi-secret, because anyone can, of course, disassemble and find your hard-coded key. But still, it keeps these nodes apart. And down here, if you have, for instance, a chat room, as I said, the chat room key, or name and key actually, is hash name plus password. So the name of the actual address here in the network is the hash of the name plus the password concatenated. And we can also make the key the same way. We can, for instance, we can just concatenate something to get another hash. We can have plus, we can call it just a string key. Then we get another hash sum that people can't figure out unless they know the password, at least if it's strong enough. So we can get a unique name and a unique key for that room. So when we connect to nodes in that swarm, we can use this key, that's connection key, instead of using the mothernet key. Yeah. That means that anyone up here who knows all this stuff still can't get into see what those nodes are talking about.
Yeah, they can see them, but they don't.
Yeah, they can see they are there, but they can't listen to them, in spite of having all the other keys. But of course, this key is probably bad because it's a human-readable password usually for a chat room. So I, of course, concatenate all the keys all the way down. Why not? When I anyway have them. So just concatenate them and hash the whole thing and get a very strong key. So of course, if you have all other keys and that's a human-readable password, you can probably crack it fairly easily. But still, it's at least one. It's slightly safer than just using that key. So I use different keys at different levels. That also, in a way, once you have connected, you immediately know, if a node connects to you, already when you start your encryption, you know that he wants to get into that swarm exactly, and not some other swarm. That means that it doesn't even have to tell you why he connected to you. You already know why he's connected to you. So as a side effect of encryption, you know what he wants. Of course, that's just saved to like 1 byte, but why not? Well, let's see. Okay. About encrypted connections, where you encrypt from the first byte. First, I'll start over here then. Can you see if I write down here? Yeah. Okay. So, the first piece of data is 10 bytes. I think you write it with a big B, right? Bytes. Yeah. Okay. And that is the IV, initial value, just a big random number. The next block, it can be different things. It can, for instance, be a standard hello message. You can just say hello, but you encrypt this with your, you take the IV and combine it with your secret key for that level, whatever level that is, and you initiate the encryption, and then you encrypt the first block here that, for instance, just contains hello. So the receiver, he will take the IV, combine it with his different keys. He has a bunch of them, perhaps just 10 or 20, not that many. Tries each one, starts the encryption and tries to encrypt this and see if he gets hello or not. And when he gets hello, he knows which key to use, and then he can keep on running like that. Actually, I don't do it like that, but that's the common way. We use, let's see what we do.
Do you have a name for that? Is there a name for that?
For this, it's encrypt from the first byte.
Okay.
I don't know any other name, but there's probably some name in cryptography, but most people, I might just call it that. Okay. And it's used to achieve stealth. I don't remember the hash space approach. We thought that was slightly clumsy, so a British cryptographer, one of the best guys in hashing in Britain, we chatted with him and he said, yeah, that's an interesting problem. I probably can solve it with hashes. He came back the next day with a very nice solution, but so I have to think about how we did it. Anyway, that's the basic principle of encrypted connections from the first byte. We do more. Then here we agree about the connection. like sending the ability hash or some other stuff. Then, or for instance, exchanging public keys with each other, because we only know the hash of the public keys normally. So the first time we connect, they have to send us the full public key and stuff like that. So we do it in here, protected by this encryption. So it still looks just random for an eavesdropper. And then, when all that has been agreed, we switch to actual heavy-duty encryption using the public keys and all that, really secure. So this part, an eavesdropper that actually knows the semi-secret key of that node can listen to that part. So the key we use here is just, it's not actually very secret. It's the one that we always publish all over the peer-to-peer network. But from this point when we go over to our RSA encryption or whatever we use, it's public key. From that point, no one can listen except the two nodes talking to each other. So we actually use encryption, well, we switch encryption here. Yeah.
And the advantage of using like a Diffie-Hellman would be that you don't have to do any exchanges, you just start talking. Is that right?
Right, yeah, something like that. Let me think a little. Diffie-Hellman means one packet less compared to our RSA, right?
But it means a whole round trip more.
Yeah, you don't have to
But
do
you can
the
do the
chatty
same
bit.
with, you can achieve the same thing with RSA, but it means one extra packet back and forth.
Okay.
Yeah. So Diffie-Hellman is slightly more efficient. And then there's also another approach now used by Bitron, I think, and some other. There is, that's not Diffie-Hellman, what do you call that? I don't think, they can actually send a random key here, not pre-agreed, and still achieve encryption from byte 1.
Isn't that Diffie-Hellman?
And perhaps that is this one. Perhaps I'm mixing up
Yeah,
the
where
names
you,
of the
you
different
both exchange a random number.
Diffie-Hellman key exchange?
Yeah, you both exchange a random number and then you suddenly have a agreed.
Yeah, that's
encryption.
also Diffie-Hellman. That's a special case of Diffie-Hellman, perhaps.
Okay.
But this one is not secure against man-in-the-middle attacks. Does everyone know what man-in-the-middle means? Yeah. But
So
it's,
someone can intercept the
you can, if you can intercept and actively change the
Yeah.
what we call a man-in-the-middle attack, you can attack that as well.
Mhm.
But if you just eavesdrop, just listen to it, record it, and later study it, you can't do anything about it. You can't crack it.
Mhm.
So it's for passive eavesdrop you're secure, but for active man-in-the-middle attackers, then you're not secure. So Bitron today uses that if you turn it on or if you are in the other end, has it too. So they can encrypt from the first byte, but it's just safe against a passive eavesdropper. Actually, this one that I use here is also kind of just secure against passive eavesdrop. Well, fairly passive. Nodes that doesn't know you've seen the secret keys. Those who know it, they can even be passive, but they have to listen to the whole network and start collecting the keys and stuff like that to be able to listen to it, which of course is very doable today. But still, yeah. Unfortunately, we can't do this much better. Well, of course, if we issue our semi-secret keys in some secure way and do lots of trouble to do that, that's in peer-to-peer network, and that's kind of hard because you don't know everyone can't have pre-agreed keys and stuff like that. So, Diffie-Hellman can also be used with pre-agreed published hashes and stuff like that. So you can protect against someone manipulating it, and then you can use it from here. I don't remember all those parts. Yeah. So, then we'll listen a little about that. Let's see. Oh, okay. A little about, we talked yesterday about anonymous networking late in the evening, so some of you might have missed it. How many here does not know what a telescopic tunnel is now?
No, I missed that bit.
You missed that part, okay.
It was at the
You
bar.
have to read up on it yourself.
I watched the video.
It's not hard to read up on, it's fairly simple.
Okay.
There are different kinds of anonymous networking. So let's look at those. Basically, the really old one is the darknets.
Can I just ask one question about the authorization encryption? So, what do you think of SSH as a protocol?
What?
SSH?
Let's see. From what I read through it when I was kind of not that experienced in cryptography, and it looked good.
Mm-hmm.
And people I know that are really qualified say it's good.
Yeah.
While TSL has some weaknesses.
Mm-hmm.
It's not exactly in the protocol itself, it's in the certificate and key handling that lacks some things in TSL. It's actually the CA structure that I think is the weak part.
Yeah, yeah.
There's some more weaknesses. But the TSL itself is good,
Yeah.
I think.
If
There's
you,
a
if you
section
use the
some-
right cipher on top of it, because the RC4 has been using TLS has been sort of cracked. So
well, the kind of RC4 they use were cracked.
yeah,
Because everyone is used to use RC4 in the wrong way.
Yeah.
If you use RC4 in the right way, it's still uncracked and perhaps one of the strongest cryptos we have. Actually.
But it's hard
but,
to use.
but there's a new attack that's just come out in the last couple of weeks, where if they can observe the same message repeated many times.
Yeah, that's actually a new one, not a new one. That's 15 years old.
Oh, okay.
There's new versions of it.
There was a new paper out just the other day.
Yeah, because they improved it.
Okay.
They improved it every 3 years. And the old one, they had to listen for several months and get millions and millions of packets. Then they were like, well, we've got it down to 2,000 packets or something.
Yeah, yeah.
That was a good improvement. Well, I could actually explain that. Are you guys using RC4? Perhaps going to use it. RC4 is one of the simplest stream cryptos that are, really simple to implement, so simple so many people know the code in their head. But it has one problem. When you initiate it in the simple way that's mentioned in the books, then the first few hundred or thousand bytes that you produce encrypted are weak. And that's actually true for most ciphers out there. So usually what you do, you initiate your key, and then you loop the initiate and do it several times internally. So you mix the internal state harder, and then it becomes strong. Most ciphers has that in their specification, but since RC4 didn't have any official statement, it was a secret crypto used by, I don't remember which authority or which, at least I think it was the American government used it, and then people cracked it by disassembling code and realized, this is how it works. But since they didn't read the officials, they didn't realize that they had to just do an extra number of loops inside to really mix the internal state. So what you do if you know RC4, you do the initiation and then you just produce like a couple of thousand bytes from this and just throw them away. Then you start using them, and then it seems to be one of the most secure you can imagine. So it actually has one of the biggest internal states of any kind. It's faster than pretty much anything else. Well, there are some that are far faster now.
It's I think it's because at the beginning the probability of repeating sequences is higher.
Sequences that are similar to the key, they give away the key. Yeah. If you look at it, you can even for me who's not a professional cryptographer, not a mathematician, I can see. Yeah, I see it's not mixed enough.
Yeah.
It's not properly mixed internally. So you have to just run this. Let it produce some random bytes and throw it away. Actually, it's probably enough to produce like 2,000 bytes and throw it away. Let's just 8 loops, extra loops. But some of us we do more than that, because I talked about key strengthening before. That you can take a key, even if it's not a human readable password, it can be any key, and with a hash or something loop, make a lot of work for 1/10 of a second or 1 second, and make a harder, stronger key. You can do the same with the RC4 and other cipher. You simply loop the internal setup routine for 1 second. So if an attacker has to take a key, loop for 1 second, and see if he can use it or not. So the attacker will have to spend 1 second on every key he tries. So you can use the internal mixing operation in RC4, for instance, to get a stronger key and waste 1 second or 1/10 usually, because you don't want to stop everything for a second. So I measure how many loops becomes 1/10 of a second, and that's like 50,000 loops or something like that of the entire mixing state. So I throw away, I don't remember buy some throw away, but that's a lot. So why not? Well, yeah. What did we talk about? Yeah. So why if we use the bad kind of initiation, and all other systems like TSL used the bad? Well, it didn't really initiate it properly. So unfortunately, that gave RC4 a bad reputation, but that was just kind of incompetent by its users.
Yeah, because it was the same similar attack that undid web for Wi-Fi.
Yeah, it was the same problem.